Okay, so let's get started. So we are going to talk about, continue about the large language model. So today we'll talk about alignments, reinforced learning from human feedback. So originally it was planned for 2 lectures, but now extend to 3 lectures. So we will skip a lecture. Yeah, today we'll talk about the basics. Basically, this is a continuation from a while ago, a few lectures back, about instruction tuning. So typically when we train these large language models, we have both instruction tuning, pre-training, instruction tuning, and reinforced learning. So this is usually a step which is after instruction tuning. And essentially this is for alignment with human preference. So that's the idea. So let's just recall the basic setup. So yeah, so basically we'll cover roughly 3 papers. Mostly we will talk about the main concept actually is talking about the first paper. So that's before the GPT-3, so that paper. This is basically get all the ideas already. So we will, all the main concept of what this is actually coming from that paper. The other 2 papers are how that applied in practice. So we will talk in more high level, less detail. And yeah, the instruction GPT is kind of a ChatGPT. Roughly, ChatGPT followed with the same thing. This one probably is a little bit before ChatGPT, but I think the difference is only scale. So ChatGPT probably a little bit larger scale when you do the instructions and so on. Otherwise, the methodology is pretty similar. Then the second one is, if you recall, for the instruction tuning, we have different ways to get data for instruction tuning. Either using human curation, which is costly, we mentioned, and a lot of people switch to self-instruct type of style. So basically using GPT to generate the data to train instruction tuning. Here is the same. So we can use essentially the data, which is using the reinforced learning instead of from human feedback, can be from AI feedback. So essentially, yeah, this is the idea, which also have other follow-ups. There are a few ideas which I still use today. So yeah, so we will talk about that. So these 2, but those are more applications. The basically principles already in the first paper. So essentially we will mostly cover that for the methodology part. Okay, if we recall, this one we talked about before. This is more for the ChatGPT. I think a few years back. Now there are some more refined the pipelines than this, but roughly this is a pretty representative even for today. So you have a pre-training, right? So and then you do kind of instruction tuning, and then you do this reinforced learning from human feedback. Then you deploy the model. So and we already talked about the instruction tuning. So basically just format, and then we will talk about RLHF this time. So pre-training is training on a large text data set. So that's the main ideas about pre-training. Essentially, they use internet data and so on. So typically, it's yeah, it's many tokens. It's trillions of tokens. So that's the size people doing pre-training now. Instruction tuning, we already seen that. It just fine-tune the pre-trained model so that it can follow human instructions. Essentially, this is something which can train a model which doesn't follow instruction well to a model which can follow instruction very well. Also, there is, if you recall the lecture we talked about instruction tuning, there are also other things which can get a large number of tasks, NLP tasks, so that they have ability to do task generalization and so on. So instruction tuning is extracting some ability more or less already in the pre-training, but just guide that so that it knows when you have a prompt, what it actually means, so that they can. So you don't have a lot of data. You don't need a lot of data. Typically, millions or whatever would be sufficient. So this is a much smaller data set. So this is for the instruction tuning. Then there is another step. So even you have instruction tuning, usually you need another step, which is what we are talking about in this lecture. Basically, this is called reinforcement learning from human feedback, RLHF. This further refine the model, but with a different type of data. It's mostly with preference data. We will talk about that when we talk about the preference data. We'll talk about that soon. And then you have a better ways of formulating. It also enforces other things like safety, like healthiness, and so on. So they try to. It's a more further refinement. So then it can do a better job refining the styles of your chat than the instruction tuning. And this is also it's pioneered pretty early by OpenAI. So they have these ideas quite early in the paper is 2019, right? So it's far before before the GPT-3, before the ChatGPT and so on. But this is what it is. And of course, deploy, you just deploy the model. This is targeting for the chat applications. I think that this lecture and the next lecture both talk about this preference data, RHF, and so on. Today we're mostly focusing technical party model, reward model, and next time we will talk about the policy learning. But now there is another thing in the pipeline, which is not here, is you use reinforced learning, but instead of RHF, which is more try to have align with human preference, you are giving model more capability to solve a difficult problem by inserting reasoning capability, right? You're training reasoning models, so that will be the third class. So this will be the last class of part 2. So we will talk about that in the third class. And they have a slightly different, and they will change the pipeline a bit as well. But nevertheless, so this is roughly what you expect how to train a model. This one just recall. I think we mentioned before. So this we just revisit this thing why pre-training alone is not enough, right? So pre-training teaches a model to continue text. It's a text continuation from prompts you could. But it's not the same as follow user intent. It's mostly from a lot of data from the internet. It's not in a style of question answering. It's just a continuation. They don't particularly know what the human wants. So that's why we need to do some post training to. But all the ability, the text continuation ability is there already. So essentially, a pre-trained LLM, a likely continuation from internet text, but something like instruction tuning tells that what a task means, right? So if you look at the self-instruct or all the instruction tuning data, sometimes they give examples, tell them what they mean, or where they try to have certain ways. So basically, after those training, they know when you ask questions, what they like. For example, if you say write a summary, they know what you expect and so on. But another aspect to slightly orthogonal related, but orthogonal to the instruction following is that you want the output to be helpful, like truthful and safe, right? Also, you want to have a certain tone to be presented in your response. So you want to say it nicely, certain things you don't want to say, and so on. So those are more people say alignment. That is more to do with this, basically is helpful and safe and so on. This is more to do with RLHF using a slightly different type of model, right? And certainly, the pre-trained model doesn't do that as well. They could have a hallucination. I mean, even after post-train, you could still have hallucination, but it will significantly reduced. You can ignore the instructions, so it doesn't do instruction following, right? Or it produce inappropriate answers. The ignore instructions, this is where instruction tuning comes in, right? SFT. But the producing appropriate answers, this is mainly addressed, could be partly addressed in the instruction tuning, but mainly addressed in this RLHF step. Right, so basically, yeah, these are two things, right? SFT is mainly for a lot of tasks, expose a lot of tasks, what human wants from those tasks when they ask. And RLHF really means you want to something a little bit softer, helpful, it's safe, right? Something you like, preferred over some not preferred. Here are the two types of human data in RHF. Basically, okay, the first is SFT, which we already talked about before. So in the instruction tuning lecture, so we talked about SFT formulation. You have a prompt, you have an answer, right? Answer just continue writing the prompts. So, but essentially, you put them together. This gives you the instruction following ability. This is a question answering. You can do that in this way as well. So this one is more like similar to the instruction following example, but for the RHF, usually you are giving preference data. This is particularly useful for the alignments, for the style difference and so on. But here, given a similar type of example, you just say, what is the capital of France? You could answer, I mean, it is known for Eiffel Tower, which basically is an indirect answer, right? So it's, this is you want a direct answer. You want something, the capital is Paris, then you say, okay, considering these two answers, I will choose the preferred, which is the first answer, direct answer, than whatever, it doesn't directly answer your question. It just talk about something which is related, where it's not incorrect, but basically, this is a difference. So for the RHF, we will focus on the preference data. There are actually other forms of RH. Sometimes they use absolute rating. So for example, you just say, okay, I give a rating as a 1, 2, 3, 4, and so on. That sometimes you see those data, but most data you see in the RHF will be this kind of preference. It could be multiple choices. It could be answer 1, 2, 3, 4. Right. In the original paper, they have a 1, 2, 3, 4 instead of 2. But nevertheless, you have a ranking of these basic one is preferred, the other is not preferred, and so on. So basically, yeah, this is a type of data file. The first data format will be different. Now this is the key part, the more technical part of this class. Mostly is about the reward model. So how do you want to utilize your preference data, right? Based on the original paper, and that's also the one actually used. We will talk about a little bit more about these next time. But preference data, it only tells you which answer is better, right? And essentially, this one means given a prompt X, answer A1, just like the format we see before, is preferred over answer A2. So this is basically what it says. However, so what is a reward model? Reward model means it measures, it gives any X a pair, give a score, real score. The better the answer is, the larger the score is. It's like a rating of your answer given your X, which is your prompt. Basically measure the quality of response A for prompt X. The preferred answer should get larger. This is a score. The larger, the better. So essentially, what you actually want to say is this one is the data format, right? So when you have an algorithm, you say, okay, what is better? You give them a score. So X and A1 is a score, X and A2 is a score. Theta is a learnable parameter, right? So in our setting, and then essentially just say, if I see this one is larger than this one, then this is preferred. If equal, of course, nothing is preferred. They are the same. If smaller, then they say the other one is preferred over. So basically, this is just giving preference data absolute rating, so that you have this rating, you can just directly get back preference. The main thing about it is how do you train such a model, right? How do you train a reward model? Remember, giving a lot of preference data, you want to train a reward model so that on the training data, this one is kind of equivalent to this one, right? If A is preferred, then this one should be larger, and you have a tunable parameter, learnable parameter theta, so in your model. So basically, this is set up, and this is what a reward model is, and this is the key concept in this class. Okay, so now with that, so what is the role of reinforcement learning here? The human figure tells which output people prefer, right? But it doesn't tell me how to optimize your LLM. So reinforcement learning here is the process of optimizing LLM. So basically, there are two main steps. The first step is a reward model learning. Basically, you have preference data. Just like supervised data, you can train a classifier. Reinforced learning, you can use reward model to train a classifier, and then to classify which one is preferred over the other one. So this is a learn a reward function. Given the reward function, then this part is more like policy learning, which will be the next class. We will talk about this. Turns out that some of the policy learning method can skip this step, but we will have more comments about that next time. But essentially, policy learning means you optimize the LLM. The LLM in the RL, because that's just RL terminology, it's called a policy. It generates your answer, right? Anything generates something, it's called policy in the RL. So when we say a policy, which basically here just say your LLM is fine-tuned or optimized so that it produces answers with a higher reward. Right? You want to have a higher rewards because higher reward, the more preferred human is to that answer is. So you want to have a preferred answer, means you have a higher reward. So basically, yeah, these are two steps. Essentially, it tells you what is a reinforced learning. Basically, you have a reward learning, you have a policy learning. Okay. Yeah, this is a basic procedure done earlier, and this is what we want to talk about. And again, today we will more talk about reward learning. Next time we will talk about two algorithms for policy learning. Certainly, after next class, there's additional thing about policy learning in a slightly different context, but also RL. Using the reasoning models, which will be the lecture after next. Okay, so this is basically what we want to talk about. Okay, so that's what it is. Now, how do you learn reward from your preference data? Right, this is your data. Given prompt, you have answer A1 preferred over A2. This is our data. Then you say, okay, how do you learn reward model? So this is the reward model. Yes, remember we reward the higher the reward, the more preferred, right? Basically, I assign a probability. So this is a probability model. It's a like logistic regression in some sense. It's a classification model, right? Essentially, it's a A1 is a preferred over A2 is a E to the reward model. This one is like logits. If you think about the logits to do with A1, logits to do with A2, and you have two classes, then you have a ratio. It's like a softmax. With this two reward model, you put it the two-dimensional logits, and then you have softmax. Then this becomes your model. So this is called the Bradley-Terry model, and that is the model which people try to extend that. By the way, you can say, okay, let's try to do something more general, but this one is basically what's used in practice. So this is a reward model. A reward model essentially can be a classifier. Basically, once you have the reward model given your prompt, your answer, then you can give a rating to say whether it's a high quality answer or it's a low quality answer. So that's the way you think about that. And if you have this reward model, it's essentially binary classification. This one means reward larger. Actually, there's a probability, right? So given a probability, and this one is just say each one is larger or each one is smaller with certain probability. In the original paper, actually, instead of two outputs, it's just four outputs. So you can, but it's natural to extend. If you understand 2, 4 is just the logits with 4, right? So it's easy to explain. So we will not talk about that, but we just mentioned that. Mostly modern data, I think they are using 2 instead of multiple. So people are happy with this or chosen or versus rejected this format instead of say 1 out of 4 or something. Okay, so yeah, this is a model. How do I estimate that? Estimate is pretty simple. So once you have a classification problem, treating this as a classification, right? You have a class label of either A1 preferred A2 or A2 preferred A1, or they are not distinguishable, right? So basically, you just go and compare the reward model. And here is the reward model according to the binary cross-entropy laws on the reward function. Essentially, if you look at that classification probability, when you write a log likelihood or the maximum likelihood estimate, it becomes a logistic regression. So that is basically this one encourages if A1 is larger than A2, right? This one encourages actually A1 is larger because A1 is larger, this is smaller, this is a loss function. So so you want A2 to be smaller than A1, the overall function will be smaller. So basically, this is a training objective for this reward model, Bradley-Terry model, okay? BT model sometimes. Yeah, so this one encourage. Sometimes people use other loss functions. You say, this is a binary classification with this is my classification score. So I could use other loss functions. Yeah, so there are proposed other loss functions in the current literature, but this one is the more standard ones we talk about. You can think about, let's say, what about the SVM, right? Or what about the hinge loss and other loss functions? They do appear in the literature, which is not too surprising. In recent literatures, people explore those losses. But still, this works well, and this is basically what we will focus on. Learning policy. We will just quickly mention this one. We will talk more in the next 2 lectures. Today, we will mostly focus on the reward model and the general pipelines. Next time, we will talk about the policy learning. Learn policy is basically, we just mentioned it, right? So it's a learned policy is a fine-tuned that generates a response from X, right? We'll give the general formulations, and we will remember this formulation go to the next time. We'll motivate, next time just motivate this policy, but we will not talk about the algorithm to actually learn the policy, just give the formulation. So you have to think about what is a good policy, right, in LLM. In the classical reinforced learning, not generative model, not in that application, people say, oh, the policy give the largest reward will be the best. Certainly you want to have a larger reward, right? So certainly the high quality response means high reward. But this is not the only thing you care about, actually, in the LLM. You have a trade-off. So what is the trade-off? Typically, as a generative model, you should produce diverse response. You don't want just have the same response. You always want to have a controllable, like a temperature. And when the temperature is non-zero, you shouldn't just give a fixed response. Otherwise, everything is deterministic. If you want to say, I want to write some novel, given that it just every time it's the same. So it's not good. The other thing you also want to talk about is learning the right knowledge, which will comment later on. Yeah, the knowledge wise. To learn a good policy, we should balance reward and diversity. So that's the first thing you would think about. And that's actually people measure that. This is something people do measure about. They do not only measure reward. They want to measure this. So how do you measure these two? Right. So reward diversity. Reward versus diversity. Certainly for the reward, we know that it's actually pretty simple to measure. It's just the average reward. So they say, okay, I look at my prompts, right, from whatever the distribution you have in your. It could be customer data if you are deploy chat on the online, right? So, but basically there's distribution of prompts. This one is your response from your LLM, right? So you generate a random response. It's never deterministic. And then you say, okay, what is my reward on this? The higher, the better. So this is something you want to encourage. So this is basically on the quality of your response, how aligned with human preference. The second part is diversity. Diversity typically you can measure by entropy. If you this one is a more information theoretical, but roughly speaking, if you have a flat response, basically every all possible token get the same response, then you have a large quantity, right? The largest possible quantity will be log of your vocabulary size, the number of tokens. Otherwise, the smaller, the more deterministic, the smaller. In the end, I mean, if you are completely deterministic, it's zero. Entropy is zero. So basically, this is typically measured by this quantity. So you can balance these two. Both the larger the better, right? So you want to have a larger entropy, you want a larger reward, but of course there are conflicting goals, so you have to do a trade-off. So that's the thing. How do you control entropy? Of course, you can use this to control entropy, but people generally not use this to contribute entropy. The more frequent one used is KL. We'll come on. We'll soon get that, and I will explain why. It's not just using this to control entropy. So for the training, right? Another thing in the piece I want to say before the training, that's why we want to say, well, eventually all this leads to how do you train a policy given the reward model. You have a so-called reference model. The reference model you can think about the start before the RLHF training, before this paraphrase preference policy training. It's an LLM. It could be after your instruction tuning. And typically it's after the pre-training and after the instruction tuning, but before RLHF. At this stage, you want to say this is a reference model. What this model has properties, right? One key is it has reasonable diversity, right? It also really says things sensible. It's already gained the instruction following ability, already gained the reason they have knowledge. They have a diverse response, reasonably diverse response. right? It's a little bit constrained, but it's also it gives a good continuation. Usually it's not, at this point, it's not well aligned with human preferences. It may not be safe, and especially if you measure this number, it could be relatively small. It's not as large as possible, as large as you want. So basically, yeah, you have a smaller reward, but you have a good diverse response and also have a good pre-trained knowledge. During RFF training, so what happens is the reference goes to you learn, but this is policy learning. So after you're learning reward, now I'm assuming when you do the policy learning, right? This guy goes to pi, and what happens, right? Average reward typically will increase because this is kind of the goal. The primary goal is to improve average reward. You also don't want your entropy to drop too much for the RL training. But the other thing, what happens is pi moves away from this guy because it goes further away. So that's a typical setting. Yeah, basically, once you follow away, there are two things happens. One is the diversity. I focus on diversity here, but also the way of going away, typically reward goes up, right? This is your training. Starting from here, low reward, good diversity, but high reward, lower diversity. But in addition to diversity, there's something else we'll be losing. This one has a good broad knowledge. Once you train, typically the knowledge is starting to lose. This one is same as when we see the fine tuning. They have weird, strange behaviors like repeating the sentences and so on, right? So starting. But essentially, both diversity and you also lose some knowledge. So this is both are undesirable. So you are good desirable, you have a good reward, but undesirable is loses diversity. Try to give you the same sentence. So also sometimes it's not good in that it's lose a little bit of knowledge before. So a diversity are true about KL using KL, which basically means pi should stay close to pi ref. You do not want to move too far. Otherwise, you don't need pre-training. You just say, I just go as far as away. But so basically you want to have a close to the pre-trained model. Don't go too far away, the RHF, but you also want that reward to increase. Two things happen when you make close, right? One is the diversity goes good. You still have good diversity. The other thing is that you also retain the knowledge. So that's why you not only just say I want to just have an entropy, but I want a KL. KL is a little bit like this: prevent diversity, preserve diversity, preserve pre-trained knowledge. Here is a KL. KL actually is the smaller the better, right? The KL is just how close pi and the pi ref is. This one just say given this training and log these two. The KL of these two policies will be because we call it policies because in this RL literature, right? The LLM generators called policies. They are the 0 is the smallest. It's always non-negative, right? KL. The larger, the actually less, not better, the larger, because you want to close. So you want to close to be this one to be as close to 0 as possible. So this is basically the case. Yeah, turns out this is the objective. Actually, one nice thing why people use KL, there are multiple reasons, but one thing is if you look at this, you have pi log pi, right? Entropy is negative this. So essentially when you say this is small, pi log pi will be kind of small, which is a negative log pi will be larger. So basically you also directly encourage diversity. So small KR help preserve diversity of trained behavior. So basically this is what is Yeah, what is, and the KL is pretty natural, yeah, especially they have a part of that, actually part of objective is kind of related to the entropy. Okay, so this is basically what this is about. Then we can move on. So one thing, what happens with KL, right? So another thing happens why you want to KL to be closer is something called reward hacking. That actually happen quite a bit, and there are ways to address that using iterative methods. But basically, when you see that when your KL increases, one is certainly lose diversity, but the reward actually doesn't not necessarily getting better. So even you are optimizing reward, right? This one is your training reward model at this point. Basically, this one, let's say on your training data, your reward is keep going up. On the test data, when your attribute is too large, they starting to go up and then go down. So basically, this is a nice regularization condition from that point of view. It helps prevent reward hacking. In this graph, you probably want to go this stage, right, instead of keep going up on your training reward. Training reward will still keep going up, but actually the actual reward is going down. So basically, yeah, this is what actually is. This is a typical phenomenon. And something which another benefit about you put this KL diversity, KL. So KL is this term you see quite often in the RL and the LLM, and we will talk about this again in the next lecture and in the lecture, the lecture after the next lecture. So just remember this reference is the one before you are doing RL, and you don't want to go too far away from the reference. You want to constrain this kind of regularize your policy so that it stay close to the reference. But within that close, you are keeping increase your reward, right? You can measure this either by one is a reward versus a KL curve. The other one is a reward versus diversity curve. But people looking at the reward versus KL curve, this one again is in this paper, they say, okay, this is a KL, right? Parental front means giving all the sort of training parameters, whatever training parameters, you can draw different training hyperparameters. Then you see either by number of steps, learning rate, whatever other things. Then you look at the reward, right? You are looking at KL. KL, of course, smaller the better. The hope is you have a very small KL, you have a very large reward, right? So basically, the left top left corner is the more moving toward this direction, the better. So you're going through all the possible parameter settings in your training, and your policy train the optimal frontier. So there's trade-off, but basically when you increase reward, you have also need to increase your KL, and you want to say, okay, I will stop here. The reason is if I go in further, the policy goes too far away from my base model or reference model, and this one is the one which had the best trade-off. So if you look at these few models, you want to have one with highest reward with certain constraints of your KL. Okay, so basically, yeah, this is something you have to keep in mind. There's a trade-off. You do not want to move too further. Quality. Loss of diversity KL, of course, there's also preservation of your pre-trained knowledge in addition to diversity. Okay, so let's continue. So a common method, given these two, here is the key, right? All we want to talk about the policy learning is this formulation motivator. How do you use reward model in your policy? Turns out we don't care about the reward model. It's just intermediate results. We all care about policy. Basically, policy is a LLM you want to use in your training. Essentially, it's like ChatGPT, right? So, yeah. So basically, this is a way to optimize that. You have a higher reward. The higher, the better. This one is negative of your KL. You want to maximize negative of KL means you want to favor smaller KL, favor your model to be close to a reference model. So that's the formulation. We will come back to next time, and also to some degree the after that time. Yeah. And how do you optimize that? This will be the topic of next class, right? Now this class, but now we are derived. We first talk about how do you learn reward model, then how do you use reward model in your coming out with objective. This objective is to train this policy. And of course, in the OpenAI, the at least at that time, they use also a lot of our algorithm. They use so-called PPO, which we'll talk a little bit about. Our focus is not on PPO on this class because it's more complicated algorithm. So they use PPO to optimize that. You just say it's just policy learning algorithm. We will talk in a high level in the third lecture, but not giving too much details. We will focus a little bit on another algorithm, a more simpler algorithm. But here we will also focus on simpler algorithm than PPO. But PPO is a little bit more complicated. But basically, yeah. So the classical algorithm in this or in the OpenAI papers, you see they use the PPO to solve this problem. You first learn reward. After you're learning reward, you use PPO to solve this. This is RL. Why this is RL? Because your data actually generated, we will see that more clearly next time. The later is here generated by your current policy. Your basically your LLM both generate the data and optimize the data. So it's not just given by something else. It's given by the data generated by the policy. And the rating is by your reward. Because you have a reward model, you can determine whether your generated policy is good or not. So basically, yeah. Generation quality, right? It's here. Balances two aspects. This is close to preference model, right? And the close to reference model is here, right? So basically, we talk about that. Essentially, this combine these two together. Beta is a trade-off parameter. It's just a trade-off. It's a regularization in the class. And here I just write it more clearly to say, oh, this is negative entropy, and this is another term, which but the overall make it closer to reference model. But on the other hand, if you just look at this term, it has an effect of this is a negative policy, but you are maximizing minus this one, right? So basically, you are favoring large entropy. So in this automatically encoded in your lecture, yeah, in your objective function. So encourage larger entropy, encourage more diversity, and so on, because of this decomposition of your KL. So anyway, so this is an objective function we will come back to later on. Here is the overall settings, right? In the original paper, then we will see how that applied in practice soon. The overall setting in the original paper basically say, okay, I have context, policy, continuation. Basically, it's a prompt. This is in that day. I'm not sure if they call that prompt at that time. Probably not. Probably the prompt, the terminology coming out later. So that's why they call it context, policy, continuation, right? So this one is probably GPT-2. It's not even GPT-3, recall that. So this is a reward model. They have reward times 4. Basically, they instead of rating 2 answers, they're rating 4. But in our practical purpose, it doesn't seem there's too much advantage of rating 4. So nowadays people use 2, right? So, but at that time they have rating 4 answers, and then you giving your data preference data with 4 answers, you can learn a reward model, right? This is a cross entropy loss, right? And this is a human label, and so on. So basically, this is a reward model pipeline, and the formula is given the Bradley-Terry model and entropy, the cross entropy optimization. Policy training, you have a context, right? You have a policy, you have a continuation. Again, this is a prompt, this is your response or answer. Then this reward model is learned from here, right? So basically, using this one, you have policy training. At that time, they use They use a PPO, but we could use other things we will talk about next time. Reward and loss and so on. So yeah, so basically this one we'll talk about more detail next time. But this is basically the two-stage pipeline: reward model learning, policy learning. Okay. Okay, good. So we want to talk a little bit about the two more practical paper. How do you use this pipeline? Without talking about policy learning, we will first talk about assuming you have policy learning algorithm, in particular PPO. That's what they are doing. How do you train a ChatGPT, right? Just from GPT-3. GPT-3, we know that it's just the pre-trained model. It can do continued writing. At that time, it can do test writing well, but it's not quite doing well with chat applications. Chat really is starting, actually revolution that will change everything is from ChatGPT. InstructGPT is more or less the recipe for ChatGPT, so which is published actually by OpenAI. It's a 22 paper. I mean, actually ChatGPT around that time, right? It's just this one is probably a few months earlier, I would say, than ChatGPT. ChatGPT is I think it's around the time of NeurIPS. So basically, this one is NeurIPS paper, but ChatGPT itself is around NeurIPS. It's probably in November or something released. This one is writing the paper probably a few months earlier. But nevertheless, essentially, you just say, okay, how do you make a GPT-3 into a chat application? Right. That's what it is. This is a milestone. We started with pre-trained GPT-3. So this is the pipeline we talked about is basically the pipeline given in this paper. We do supervised fine-tuning, right? SFT, which is instruction tuning, using human demonstrations, or basically, again, later you will talk about the self-instruct. You could use the instruction, self AI. Reward model using the human preference data. So these are two different data. We talk about that. One is demonstration, just one answer. The other one is two answers. You prefer one over another. Policy learning is using PPO, which we will talk not next time, but we will say a little bit about this. We are not focusing on this algorithm with KL penalty to stay close to SFT. Basically, the reference model is after this SRT, right? So that becomes a reference model before this RHF step. So yeah, so hopefully this is clear, and here is what it actually looks like. Actually, yeah. So I don't know why this prompt. Yeah. So basically, instruction training pipeline here is demonstration data. This is policy. I think maybe I don't know why there is no probably something wrong with this display. I will double check, because there should be a step 3. Optimize the policy against the reward model using this. So this one, you collect demonstration data, which basically instruction tuning data, right? You essentially this alike, and some people want to do more and so on. So basically, this is your instruction. This is what your looks like. And now you have FFT data, which is earlier lecture. It's basically special formatted data. We will have our homework. Just play with a little bit of these. Then you have reward model, right? You train your reward model preference data. This is ABCD, which means they still have the 4 choices instead of 2, but you can do that with 2 choices. Then you just read that. Using that, you can use the Bradley-Terry to train a reward model. Okay. So basically, yeah, this is their preference. This is whatever. So okay, so this is something like that. And then optimize policy against this reward model using reinforced learning. This is something here, except yeah, I have to check why it's not showing up here. But anyway, so this one is the next time we will talk about. But anyway, so again, here they use PPO. So we will see immediately they are using PPO. So Now let's look at the results. So this is more application. Instruction GPT results, right? So you can think about this as ChatGPT. So you have, this is a GPT. This is basically GPT-3. One is a GPT, basically GPT-3. Oh, sorry, this one is GPT-3. Yeah, this one is a smaller scale. But you can call them all GPT-3, but with different scales. The largest GPT-3 is 175 billion. We know that. This given in the earlier paper. And then GPT prompt, which says you have a right prompt engineering, you can get better results, right? So basically, this is after SFFT. So basically, instruction following, instruction tuning. So this is after BFG, you get this. This one is a 2 PPOs. So what are these 2 PPOs? Basically, 2 PPO is, remember we say that one thing we want to careful about is once you do too much training, they will starting to losing your ability in the general data. So this one just say mixing with pre-trained data. PPO, TP is essentially the mix, training mix, right, with pre-trained data, pre-trained training mix or something like that. Basically, yeah. So this one states say you do the PPO training, but you also add some on the pre-trained data rather than all this. So that make it more stable, less forgetting. And clearly, if you look at that, it's a small effect, but at larger scale, you could have a little bit of improvement for that. One notification, what's interesting is the following, right? So if I start with a very small model, right? I do all these steps. Each step is increasing. So this guy, prompt is helpful. And we know prompt is helpful, of course. And then instruction tuning is helpful, which is not surprising. You say, okay, this one is also helpful. But let's say we start and compare. This one is where you can say, as a chat application, which model's response is preferred. If you look at untrained GPT-3, largest GPT-3, versus a very small model, right? This one by far is better than this guy. Yeah, and then basically, yeah, okay. The base model is compared with this guy. They call win rate. Just say when you compare the 2 responses from this 50%, right? Basically, this one is instruction tuned this guy, right? So here, so the larger the better. If you win, the better. And in the homework, we will do some win rate calculations as well. But basically, yeah, basically, case itself is 50%. But for the others, they can get, smaller model, 1B, much smaller, could have a better response than a high, very large GPU model, even with the instruction tune or without tuning, right? Even after instruction tuning, if I apply something, if I don't do any RHF, right? Versus something I do RHF here, much smaller model, smaller window wins. So this is something which actually learns something which human prefers, which clearly indication about that. So from this paper, one thing you should understand is a human, this one is OpenAI. They already have an API at that time. But the metric following about outputs preferred over this guy, right? And error bars is 50%. But essentially, I think what's interesting is RNHF has made a significant outperform GPT-3 baseline, even much smaller model. So that's actually quite surprising. You are thinking about a much smaller model, it has to be not as good, right? But it turns out the training pipeline is more important than model size instead of less important, particularly for the chat application. So this is what you can get out of this. Yeah, yeah.
The PPO, PDX, and the
yeah. This mentioned here. It's basically one is PPO just on their PPO training data. We will see their training data. The other one is mixed with pre-training data. Just make sure it doesn't forget as much. So they add more data. The data comes from pre-training. Yeah.
Explain why there's a trend like this.
Trend like this. What do you mean? I mean, the trend is model size here, right?
Why as the model size increase, the POPDX?
Oh, that I don't have too much knowledge why. Yeah, but you know, this is basically what they observe. Yeah. So yeah, this is just empirical. Yeah. Yeah. They just say, you know, this can have a difference, and somehow, yeah, it helps probably a little bit. Yeah. For the larger size, especially. But anyway, so but you know, these two are small. So for the R training, it doesn't seem to lose too much ability. So that's a good thing. Yeah. Implications, right? So if you look at these pictures, right, what you can say about that? It turns out RHF is important. That's basically what one sentence knowledge, right? Alignment more than the model size, because you know, you just look at even after the instruction tuning. Turns out at that time, Google doesn't do any RHF. They just looking at the instruction tuning. So all their models at that point only instruct. But you know, based on this one, the OpenAI's model of a much smaller scale could do better for chat applications. Again, this is for chat applications. Yeah, alignment matter better than more than raw model size. Post-training, it's important for user experience because this is, again, it's for chat applications. Large model prompt is not enough, right? So match the RHF. Turns out RHF is more important in some way. Yeah, SFT can be further improved. Basically, no, they're just repeating about which are mentioned. Yeah. Aligned small model can be more useful than much larger base model. So this is for the chat applications. Okay. Okay. So now let's look at their data. Just quickly talk about where their data come from, this data, and then you can get a rough idea about the ChatGPT data, which will be kind of that. I mean, here is the SFT size, right? So yeah, the data size is the number of prompts. So it's you can think about this one is yeah, it's 10,000 prompts training, right? Both from you know, outsourced to the labor, or by the customer. They are customers' distribution, the prompts, and then you can have so they have a smaller number from their prompts from customer for the SFT, because I think they just want to broader their task diversity. So and then yeah, and then basically, yeah, basically this is what their distribution is. Reward model, again, you have a distribution, but now you are seeking more. So this is SFT. SFT is less to do with customer data, their API, than the alignment. Alignment is more, as I mentioned, is more to do with the chat application, right? It just favor what favor. So you see a significant more about that with customer. On the PPO policy training, they are totally custom. So this is something I'm just want to mention instead of other things, because you know, you just see this is general ability. They can handle the let's say the outliers or whatever, right? So then you want a lot of other data sources not necessarily occurred in your immediate customer data. You're feeling a lot of other knowledge, but this one is more about the preference, customer preference. This one still complemented with other data, but this one is pretty much all customer data, because this one you are thinking about training a ChatGPT, right? So you want to say what customer like. So basically, yeah, this was you can see that immediately. This RHF is for the chat applications. Use many more labor written around the customer prompts, right? Reward model, you multiple outputs, training size much larger. This one you need a larger actually, and the PPO use only customer data. Basically says you know, you want to train a ChatGPT, you want to favor customer. So that's what it is. Model size. The other thing which would be interesting, I just quickly mentioned that, is the reference model is this guy, right? So this one we mentioned before. This is a policy during the RHF updated using PPO, right? So basically, this is something for the policy. For the reward model, what is interesting is the following, actually. It's much smaller. First, it's initialized, again, with the SFT model, but it's a much smaller size. And we'll soon give the model size. The final on-embedding layer, which basically is output layer, right? Decoding layer is removed and replaced by scalar reward head, which is pretty typical, for this reward model. I think we will do that as well. So in the using a pre-trained model and do a reward model and so on in the homework. And then you as input and output the reward, right? So basically this is what it is. And the reward model size actually is a 6B. So that's much smaller. Turns out it's a significantly reduced the training cost because they have a larger training data. But nevertheless, besides the training cost, they also mentioned this, which I found interesting. It's not explained too well. Basically, larger reward model found computationally expensive, sometimes unstable in training because your training data is small. So basically, that's what they said. But usually, even nowadays, when you look at the reward model, you usually don't have a very huge size, not like this size. It's more like this size, sometimes larger. Nowadays, reward model could be more than this number, but usually it's much smaller than the training data. You do not use a huge reward model. Reward model is much smaller. So this is something which is good to keep in mind. You don't need a huge reward model, right? So, yeah, this is about the summary about their paper. Any questions about their paper? How the JetGPT is trained? Yeah, yeah. There's another thing about they have other evaluations. Yeah, I think basically other evaluations says that you are you can have a multiple objective. Nowadays, reward training, they also use multiple objectives. This one is actually their metadata. They evaluate with multiple objective, but the reward model is just binary. They do not have multiple objective reward. But nowadays, when people doing reward modeling, sometimes they do multiple objective reward. This one is you can see how they care, what they care, right? Overall quality, this is a soft measure. Fail to follow instruction. This is certainly one thing is important, right? Inappropriate and so on, and contain certain contents and so on. And yeah, basically, these are just classifications. Some not necessarily to do with quality, just their classification. But the multiple aspects, right? You can look at the quality, correctness, and the safety, and so on. And they are mainly for the using analysis and evaluation rather than that. But nowadays, people try to look at the multiple objective, try to optimize that as well. Trained from price reward is just pairwise. Preference is binary reward. It's not multiple objective. What it says the following. So I just quickly mentioned this. The RHF preference data can be considered a balance of these criteria. Some are just classification, but some of to do with the criteria they care, right? Like follow instructions versus safety. For some things, you probably shouldn't follow their instructions. You will just say you don't know, and so on. So the fine-grained data will help explain instruction GPT is preferred over multiple dimensions. They try to talk about in that paper, but I do not because there's a balanced weighting of these different objectives. Better following intended instructions, better satisfying specific constraints, and likely to hallucinate, less likely to hallucinate, and more probably in the setting of a customer assistant and so on. So basically, this is something different dimensions they care about, and they all coming out with a single reward model. Human preference are not just basically they include different. So yeah, this is a quickly mentioned. Now there's now we are talking about just this is a kind of a parallel of our earlier talk about instruction tuning when we say the human creation, which natural instruction, supernatural instruction, right? If you recall that, to shift to non-human self-instruct. This is a similar idea. Basically, RHF, you still need a human demonstration. This one we talk about, you can use replace human by self-instruct. And here actually it also appeared to this paper. This one is one specific paper from Anthropic. And the human preference compared for real-world model, right? Essentially, you involve quite a bit of human RL formulation, and this one is automatic, of course, doesn't involve human. The idea is that, so, okay, human expensive is a label and slow, and it's rigid. Sometimes opinion changes and so on. Safety label is costing when objective changes. So basically these are create problems. You reinforcement from AI feedback, which is RL AIF. It's like a self-instruct for the instruction tuning. Basically, keep the same pipeline, replace part of the human. Even in the self-instruct, you need to have human judgment to evaluate, to double check in the end to say whether this forms a good instruction tuning data. But for the reinforced learning from AI feedback, you keep the same pipeline. You actually replace part of the human feedback with AI feedback. So that's basically the idea. So reduce the human labor. What they call is a constitutional AI. Nowadays, constitution is a short list of natural language rules that define design behavior. So that's basically in their setting, right? Nowadays, people using this idea actually, but they don't call that constitutional AI anymore. Somehow it's called rubrics for reasoning-based reward rubrics. You give some guiding principles for the LLM, let LLM to generate a reward decision to say whether it aligned with this principle. For example, avoid the harmful instructions, right? Be truthful about uncertainty and whatever. You need to you can give us some prompts to the LLM. The LLM say, oh, whether it's this one is good or not. They could even give a reasoning trace about, say, to explain whether it's good or not. But nowadays, yeah, this idea still is, but in that paper, this is something there. So using the SFT stage, you could do that. This one is a little bit like a self-instruct, but it's using a different style. This one turns out to be, you have a response, right? You can say, okay, let's create instruction tuning examples, which giving certain principles, say, I'm not harmful, right? I would just say, oh, I don't have. So I generate a response, and I will criticize using this LLM. Say, does this response contain harmful instructions or information response? If you say yes, then you revise. Say, okay, this is not good. Then you have to do something. So basically, it's just to keep a revision, keep response according to principal revision, and so on to create some SFT data. So you can use that in the SFT. You can also use that for the RL stage in the sense of RLHF stage, right? AI evaluate, compare two answers according to these principles to say which one is preferred. So you could do that. Yeah, basically, of course, then you can generate a lot more data this way. So, so the benefit, of course, you just write rules. And given the rules, you generate a lot of data. You can do some filtering, but nevertheless, you do not have to do this full data labeling, right? So why this works in some sense, right? You can think about that, right? So doing critique and doing this is a little bit in the more modern, say this could be, say, it's an agent setting. Generating response and critique have different roles, and this one you can argue that probably once you have some instructions, probably easier to do. So basically, once you have a response, I mean, they can criticize. Job is easier, and then they can give some feedbacks. I mean, same for the human, right? Some other people can give you some feedbacks, and so on. You improve and revision. So this style seems to be way can actually improve the response to be more aligned. So here is what their training pipeline is. Their pipeline is you start with a helpful RHF model. This basically to generate, you're starting with some human. Again, you generate the so-called red teaming. Red teaming is just try to prompts try to say try to break your safety system, make it generate something undesirable, right? But then you are giving certain adversarial prompts to give more desirable, and then you generate the prompts, generate critique, generate revision, and then this one is called supervised learning, right? It's constitution AI, so that's what they call. Nowadays we don't call constitution AI anymore, but the basic idea is still being used, just going different. And now this basically this one is SFT model. You can see boosted with AI, right? AI generated response, SFT model, and then you have now you are doing the other stage. The other stage is reward model, right? Preference model. They call preference model. We call reward model, but essentially the same thing, right? They're just using slightly different terminology. General response is pairs of examples, right? Pair examples. The reward model, of course, is this Brad Terry model. And then you have policy training, say BPO, right? So and then basically you get a final RL model. So basically it's still two stages. Supervised fine tuning, but now they can say, okay, I can use RL to do that. And here you say, okay, I can use AI to do that. Okay, I can use AI to do that, and so on. So fine tune on the revised output and so on. Stage 2 is sample 2 sentence, AI evaluate choose preferred sentence, and so on. Train reward model, then LLM policy, and so on. So basically, you just say replace human by AI. So that if you have a single sentence, that's all it is. If you look at their results, so they do have some results. Results say, okay, so starting with a base model, is pre-trained. This guy is, you can say, the traditional supervised fine-tuned model, and up to the standard RHF, right? It comes here. What they do is, again, this is a kind of ring rate. Allo certainly is a grading system. It just, and this harmless and helpful. Usually they have a conflict, right? So sometimes you have to generate harmful answers to be helpful. They ask for some adversarial answers, right? So basically, there are trade-off. Again, similar to this reward and the KL trade-off. In practice always have a different metrics of a trade-off. This is a standard RHF. You have a certain trade-off, right? And essentially, this is a frontier you can get. Here is where is I think it's just in addition to this, you're starting to do this guy, right? And then doing there's also chain of thoughts, but we can ignore that. But essentially, is say, okay, I have parental front improvement. I have RL, right? So this is constitutional, basically using so-called, in our more modern terminology, it's called rubric-based, if I have a chain of thoughts, reasoning reward. It's called, okay, reasoning reward model, rubric-based. But essentially, those are giving you a new frontier because you have a larger data, right? You can say more details, much easier to create. So you get a better frontier. So that's what they claim. Okay. Again, in the instruction tuning nowadays, a lot of things, even nowadays, you have self-instruct. They're the same idea. They demonstrate better. So eventually, you can think about it. They just self-evolve. You don't need a human, or at least you need a little bit of human in the beginning to bootstrap, but in the end, you can self-evolve. So RIF shows a better helpfulness have a trade-off, improves harmonies while keeping strong helpfulness. This is basically the same. Not only from this one, basically, I just make comment. They do still have meaningful answers, and they are saying the same thing to interpret these results. So basically, this is what they say. But in summary, right? Essentially, after pre-training, we have all you need to know is after pre-training, we have two things. One is instruction tuning, SFT. The other RHF. You need in that you have the reward model. You have a policy learning. Next time we'll get to the policy learning. Still remember that formula. So we will first starting with the particular policy optimization formula which we are given before. Right. Reward model constrains preference learning into scalar. Right. KL needs balance, reward, and diversity. So this is also part of importance in the RHF. Instruction follow GPT shows that alignment better than model size. This is actually surprising if you look at their number. But this you can use RHF the same, but instead of a human, and you have AI feedback. So that's how. And for reward model, you need to remember this BT model. Right. So that's all. Yeah. Okay. Thank you. So we're done. We'll continue with policy learning next time.